of night. You just called up my name.
Hello. Okay, please have a seat, and in general, everyone except for the speaker should be wearing a mask. I thank you for that. So good morning. I am Steve Byrne. I am the director of the Mani L. Baumick Institute for Theoretical Physics, and I am very excited to welcome you to the 5th year celebration of the founding of the Baumick Institute. Fortuitously, this coincides with Mani's 90th birthday. Unfortunately, we're a year late because of the pandemic. So we'll make believe that Mani is a young man of age 90. We are, of course, absolutely delighted that we can finally welcome you here. And we have a great set of speakers, including 3 of our young star professors who will give you a taste of the work being carried out at the Baumick Institute. We certainly have much to celebrate. 7 years ago, the Institute was a vague glimmer. Today, with Mani's vision and generosity, we have and the very strong support from the UCLA administration. We have a thriving Institute for Theoretical Physics with funds for hiring postdocs, paying graduate students, running workshops, bringing visitors and guest lecturers. This is completely energized theoretical physics here at UCLA, and I will have more to say about that at the banquet tonight. And as part of the celebration, besides our talks from the luminaries, we decided to hold a workshop on analyzing the discrepancy between the consensus standard model value of the anomalous magnetic moment of the muon and the measurement by the Fermilab muon G-2 experiment. I think most of you have heard the news about that. And we have gathered leading experts from around the world to address this. And it seemed right to us that this is the proper way to celebrate the 5th year of the Institute by holding a hardcore workshop on a timely and pressing topic in theoretical physics. And this workshop is part of the Schwingerfest series in honor of Julian Schwinger, who is a professor here for 20 years. On Tuesday morning, we will have introductory talks on the topic of the muon anomalous dimension to conclude ManiFest and to kick off Schwingerfest. And I should mention that those talks are not here. They're in Physics and Astronomy building. So our first speaker today is David Gross. While David needs no introduction and has far too many awards and honorary degrees for me to list, let me just point to one of them, the Nobel Prize in Physics. And that's for the discovery of asymptotic freedom in quantum chromodynamics, which showed it to be the theory of strong interactions. He's also one of the originators of heterotic string theory, which is a prime candidate for unifying all forces of nature. David has served on our advisory board and has helped us considerably over the past years with his advice and wisdom. Without further ado, I give you David Gross.
Okay. So this is working. So good morning, everyone. It's really nice to be here. to celebrate Mani's birthday, somewhat delayed, and the Mani Baumick Institute for Physics, Theoretical Physics. So if you actually looked at the documentation, the invitation to this meeting, you'll see that there was no title for this is in order to pique the interest of the audience. The title is actually called My Bucket List, and I'll explain that later. But first, let me start with a few remarks about Mani, whose 91st year we're celebrating. Mani is a remarkable man. He was born in a small village in India. I gather he didn't have shoes until he was a teenager. His father was a disciple of Gandhi and a leader in the independence movement in India. And Mani himself spent a summer at Gandhi's village, and I imagine learned a lot from him. He then went on to study with S.N. Bose, whom we all know as the Bose of bosons, and got the first PhD degree from IIT in Calcutta. He then did a postdoc at UCLA. The story is that his village raised the money for him to arrive here by plane. And when he arrived, he says he had $3 in his pocket. A lot has changed since then. After his postdoctoral experience, he went to work for Northrop, where he developed the excimer UV laser, which turned out to be instrumental in enabling laser eye surgery, LASIK eye surgery, as well as etching chips from microelectronics. Mani is a deep thinker, a generous donor, and a good friend. So, oh, right. Where am I did that. Sorry. So Mani's philanthropic contributions have been largely to physics. But also, he established the Mani Baumick Educational Foundation in Calcutta, which enables young people who are disadvantaged but brilliant, much as he was, to continue to work in science and technology by providing them full scholarships. So I had the privilege of joining Mani 5 years ago at the 15th anniversary of this foundation and participated in the ceremony where all these young people would come up and get their awards. It was really a very, very moving occasion. Mani also established intends, I think he still intends, to establish an international center in advanced research in Calcutta. But India is a difficult place. And during my visit in 1917, it became clear to me that it's very hard to establish advanced research institutes in Calcutta, much harder than in Los Angeles. And I made some remarks about the difficulties in my speech at this meeting, which was picked up by the press. Nobel thought, red tape stifling talent. Well, that was intended to try to push the local government and the officials to facilitate the establishment of Mani's center in Calcutta, but I don't think it worked. India is still a very difficult place. Not the case for UCLA, which has cooperated with Mani and with Svi, who had the idea of establishing a similar research institute at UCLA to create what we're now celebrating the 5th year of, a very successful Institute for Theoretical Physics. That was established just about 5 years ago, right? And is flourishing today, as you all know. So what can I say except happy birthday, Mani? Okay, now to the bucket list. So there's a tradition in this country that when you arrive at a certain age and face the unknown, you make a bucket list. This is a typical bucket list you can find on the internet. People want to do this before they depart. Skydiving, see the something or other, paragliding, learn something. Don't know what. Anyway, that's not my bucket list. My bucket list is more related to the questions that face us in fundamental physics. So 18 years ago at the 25th anniversary of the KITP, I laid out 25 questions with the help of my colleagues that might guide physics for the next 25 years, which have almost passed. And that was I immodestly say, a pretty good list of questions in the sense that most of them have not yet been answered. And they still form, there's still other questions that we are asking in cosmology, astrophysics, condensed matter physics, particle physics, string theory, biophysics. Physics is a very, very broad field. When I looked at these questions again, I realized that indeed most of them have not been answered. Dark matter, I was sure by now would have been discovered in the laboratory or produced at the LHC, but it hasn't. And we still have really are even more ignorant about what dark matter is today than we were back then. Then we sort of knew what the answer was. It was a heavy WIMP, supersymmetric partner of the ordinary particles, and it would shortly be discovered and produced. Well, that's not correct, it seems. But anyway, that's too many questions for a bucket list. So I decided to instead focus my bucket list on 3 topics that I really would like to know the answer to while I'm still around. QCD string and confinement is number 1. That's a question that we started asking almost 50 years ago after QCD appeared and seemed to describe this strong interaction, the nuclear force. How are quarks permanently confined inside the nucleon? And can we calculate the mass of hadronic states and control the theory, solve the theory? The second question in my bucket list is unification. That was after the emergence of the standard model, the obvious goal suggested strongly by the nature of the standard model of all of us. We're now in a position to unify all the forces of nature. And I really would like to understand how that happens. And finally, as all string theorists understand, we don't know really what space and time is. And that's perhaps the deepest conceptual problem that we're faced with. And I really would like to understand where, in detail, where space and time come from. So that's my bucket list. It's a wish list. I'm not that confident that these questions will be answered in my lifetime or yours. Let me start with what we know. Feynman once was asked to summarize physics, all physics, fundamental physics. And he said, brilliantly, as he always did, his summary of physics. He said, if there was some catalysm, like, for example, a war in Ukraine and Central Europe that might turn into nuclear conflict, it's not unimaginable, and all scientific knowledge were to be destroyed, and only one sentence passed on to the next generation of creatures. He didn't say humans, by the way. What statement would contain the most information in the fewest words? I believe it's the atomic hypothesis, or the atomic fact, or whatever you wish to call it. And that one sentence is, all things are made of atoms, little particles, oops, these little particles move too quickly. Little particles that move around and are in perpetual motion, attracting each other when they are a little distance apart and repelling upon being squeezed into one another. It's really a beautiful summary of perhaps the essence of what we understood in the 20th century about the theory, our understanding of matter and what it is made of, and how it interacts. So I tried to do this in the sense of what did we learn in the 20th century in particle physics, but I'm not as eloquent or as proficient as Feynman. I couldn't squeeze it into one sentence. We've learned too much, but here is an attempt at one slide at least. Well, we've learned that all matter is made out of charged spin 1/2 fermions. And unlike Feynman, there's a lot of jargon here, of course. Forces are described by quantum gauge fields, which occur in 3 phases. In the case of electromagnetism in U1 gauge theory, Coulomb phase with long-range interactions. In the case of the weak interactions, SU2 gauge theory, the screened or Higgs phase, and short-range interaction. Screened interactions by a unnatural scalar field sector. And in the case of the strong interactions or the nuclear forces, SU3 gauge theory in the confining phase. So let me now turn to the last theory here, QCD, my favorite, of course, a remarkable theory. It's remarkable compared to the other components of the standard model in many ways. One of them is that it really has no adjustable parameters. Of course, when you try to describe hadrons precisely, as calculate their masses, as some of our lattice gauge theory friends do, you need to include, to have precision of a few percent, the masses of the light quarks or the heavier quarks, but that's qualitatively kind of irrelevant and a very minor effect. The mass of the nucleons arise not from undetermined parameters that you have to measure experimentally, but from the energy of the confined gluon field and the kinetic energy of the quarks. And so in QCD, to the extent that you could ignore the light quarks everything, all dimensionless parameters, measurable parameters, measurable quantities are calculable. It's really the first example of a theory that comprehensive. And finally, there are no infinities or new physics at short distances. The theory has an infinite range. It is very simple at short distances. It's asymptotic freedom. But it suffers no problems at long distances as well. And it can be extrapolated as far as you want, where not for all the other forces and physical space-time that we encounter in nature. So it's also a theory which has had impressive tests, and much to the frustration of our experimental colleagues, the amazing instruments that they have constructed and continue to use to measure what comes out of proton collisions at very high energies, continues to confirm mostly the predictions of QCD with incredible accuracy. This is and you can actually calculate the spectrum of hadronic states, confined composites of quarks. The nucleon and its partners, mesons. This was incredible accuracy. In fact, including the other very small and controllable effects, such as the masses of the light quarks and electromagnetism, one can even calculate precisely the neutron-proton mass difference. So it's quite remarkable, but not, and amazingly impressive, but not that satisfactory, because of these calculations have to be done by large-scale lattice QCD, which is in effect a numerical evaluation of a multidimensional or infinite dimensional integral. But what we really would like would be an analytic approach that allowed us to truly understand how this confinement of quarks arises and is a controllable quantitative way of dealing with QCD at large distances. QCD at short distances is weakly coupled. That's asymptotic freedom. It's easy. It's not that easy. There are communities like, which are very strong here at UCLA, and Steve Byrne and his collaborators, and all over the world, in extending the perturbative calculations of QCD to unbelievable accuracy. The experimenters need that, and the mathematics of perturbative QCD has turned out to be incredibly illuminating and yields much more than just numbers that can be compared with experiment or measurement. But it doesn't help too much in understanding the behavior of the theory at large distances, where the couplings are strong. And we don't really have a systematic quantitative control on paper and pencil. Some questions, static properties of hadronic states, can be studied using lattice gauge theory, but not scattering or the nature of the quark gluon plasma at high energies, at high temperatures, and so on. This is what lattice QCD shows if you take two quarks, very heavy quarks, so they don't populate the vacuum fluctuations, and you try to pull them apart. Instead of ionizing a meson or a nucleon, they're confined because the vacuum squeezes these flux lines that are illustrated here into tubes. And the force between the quarks and antiquarks, or between three different colored quarks and the nucleon, does not diminish with separation. So mesons, hadrons cannot be ionized. That's confinement. Picture is very beautiful, and it suggests something that actually historically happened. This meson flux tube looks like a thick string. It's a tube, but think about it as a far away as a string. And indeed, in history, string theory was discovered by trying to construct a theory of such mesons. Long before QCD, long before it was even string theory. It was a phenomenological approach to constructing observables, scattered amplitudes that would be consistent with the patterns that emerged from experiment that in hindsight are understandable in string theory and really based on this idea that mesons are flux tubes. So in string theory, those flux tubes are really strings with labels attached to them, colors of a SUN gauge theory, we would say. And after QCD came along, it's clear that gauge theory, where you have quarks or other colored objects invariant under a local SUN, if they're N colors, quarks can be described both as a gauge theory and as a string theory. Now, of course, in string theory, it was discovered early on that their closed strings had quite a different interpretation. They seem to be forced to be describe gravitons, and the quanta that describes the fluctuations of space and time, of dynamical space-time itself, of general relativity. And string theory rapidly became a theory of gauge forces and gravity. This picture is correspondence between gauge theory, QCD, and string theory. Was understood initially through a limit of string theory, where one imagined that the number of colors, N, became very large. And in large N QCD, things simplify, as often happens when one takes limits like that. If one imagined a limit where the number of colors of quarks was infinite, then we understand that QCD would be described by a free theory, a non-interacting theory, but not of quarks, but of glue balls. Large N, the quarks play a very little role. The gluons, since there are N squared of them roughly, are more important. And they, for large N, we are confident that the theory would describe totally stable, non-interacting glue balls with scattering amplitudes that were suppressed by 1 over N. Another way of saying that is one would have a classical theory of something, n goes to infinity could be interpreted as the classical limit, the weak coupling limit of this theory of an infinite number of glue balls. And furthermore, that classical theory should be described by something like a string theory. The evidence for that is partly perturbative, and perturbative QCD, or actually any large N matrix model or gauge theory, the perturbation expansion is controlled by planar Feynman diagrams, which form a kind of, can be mapped to a two-dimensional surface and look like the world sheet description of a string. We also know, incidentally, that the large N limit is not such a bad limit for QCD, and there are many features of phenomenology in QCD that can be explained by a 1 over N expansion, even though N in the real world is only 3. 1/3 squared is not a bad expansion parameter, and often the corrections to the leading large N behavior are suppressed by that magnitude. But the biggest reason we're kind of sure that there is a string theory description of QCD is the explosion of understanding of gauge theories and string theories that emerged from the ADS-C correspondence duality. So that's why I think that QCD string confinement, the large distance behavior of QCD is, well, that's why it's on my bucket list, not just because this is a question I really wanted to understand 50 years ago. And there are reasons why this might be an appropriate time to do that. Over the last 50 years, there, of course, have been incredibly major improvements in our understanding of both quantum field theory and string theory and the relationship between them via supersymmetric gauge theories and their phases, branes, the important role of branes in string theory, and of course, ADS-CFT. And recently, there's been some very interesting progress on the effective action of long confining strings. So if you have a theory with no dynamical quarks, or for large N, in any case, the quarks are suppressed, and you pull a quark and anti-quark very far apart, if there are no quarks, dynamical quarks, it won't break. And the dynamics of that confining string, large confining string, is quite universal. And a lot has been understood about its universal features. And more recently, there have been some very interesting developments understanding the specific dynamical effective string that theory that would describe the oscillations of this long string in the case of QCD. There's also been, over the last decade or two, a great increase in our understanding of the symmetries, generalized symmetries, anomalies of quantum field theories in general, and the mechanisms that could be responsible for confinement. We also have developed new analytic tools for studying quantum field theories, namely the bootstrap approach, which has been very successful for conformal field theories and is now a powerful tool in exploring the nature of quantum field theory. And then there are lots of prospects for novel experimental probes of hadrons. First, there are new hadronic states, tetraquarks, and other bizarre exotic states that have been discovered recently at the LHC. And they offer a challenge and perhaps insights into confined hadrons. And the electron ion collider, which will really probe the structure of nucleons to a much larger degree than we have available at the moment, is coming on soon at Brookhaven. And then, of course, there's the maturity and power of lattice gauge theory, which has proven so successful and is now a powerful tool that could be used not just in trying to calculate the mass of hadrons or G-2 form factors, but also as a tool in trying to understand the dynamics of QCD. So it's perhaps appropriate to check off that item in my bucket list by a concerted effort to better understand QCD and other strongly interacting gauge theories. And a group of us at a KIT program last year decided that makes sense. So we turned to the Simons Foundation. And yes, last week they announced Simons' collaboration on confinement in QCD strings. This is the logo of our collaboration. It's led by Igor Klebanov and Ofra Aharoni and Serge Dubatsky. And I'm part of it, and I hope it will remind the younger generation in particle physics that this is still an open problem that should be on their bucket list as well. So now let me turn to the second item on the bucket list, which is the unification of all the forces of nature. Now, it's clear that the standard model, which is so incredibly successful, cries out for unification for many reasons. There are various gauge groups fit so neatly together. And when we extrapolate the standard model to higher energies, which is easy to do for theorists, at least, the forces of nature appear to unify, at least the couplings unify, as well as the representations of the gauge group can be unified in many easy ways at a place where gravity becomes important. And this I still regard as the most important clue that we have from nature, that where the scale of new physics, some kind of new physics must arise. There may be many other things happening in between, but that's a place to look for the unification of all the forces that we know. And that attempt has been going on for almost 50 years and led us to seriously consider string theory as the unification, because string theory automatically contains all these forces naturally in a consistent way, free of the divergences and singularities that plague quantum field theory in trying to describe gravity. So this has been a goal to describe the standard model with its unexplainable few parameters, and the nature of the gauge theory itself, and the number of colors and things like that that are as simply a low energy manifestation of a unified superstring theory. So I was giving this talk 30 years ago or 35 years ago. This would have been the hope, but it got clouded because although string theory in some ways is the first theory that contains no parameters, no non-dynamical parameters. All parameters in QCD are, in a sense, dynamical. They might appear to a low energy observer as parameters like the mass of the quarks, but really they're expectation values in some ground state of dynamical fields and exploring ways of getting the standard model from string theory, one ended up discovering that there appear to be an incredibly large number of possible solutions or universes. Not exactly sure what any of this means because we don't really have a string theory with a Hamiltonian or Lagrangian or well-defined answer as to what a solution is, because string theories are theories of space and time. But there appear to be many possible candidates for metastable states that look a lot like the standard model or a lot different from the standard model, and no principle as to say which is correct, if any. So in trying to address the problem of unification, I don't think the possibility that the standard model could somehow be fit into string theory is the problem. The problem appears to me what fixes the dynamics. And because it's not totally it wouldn't be satisfactory to find a compactification, some Calabi-Yau manifold or F-theory construction, which agreed exactly with the standard model, enabled us to make predictions, or they were verified. One still would like to know what is the principle that picks that one solution, that one scenario out of the infinite. There are actually an infinite number of possible, equally valid, equally possible universes, as far as we understand. Anyway, the answer to that, I have no idea, but that's why it's on my bucket list. But I think it has a lot to do with space-time, which is the third item on the bucket list. Now, we've known forever that at short distances, space and time is complicated, at least in trying to naively quantize general relativity, the theory of dynamical space-time, and has to be replaced by something else. And that was one of the most exciting applications, possible applications of string theory. In string theory, as one explored perturbative string theory, one realizes that many of the features of space-time that we have been accustomed to forever, even after Einstein's dynamical theory of space-time, such as the fact that we live in a smooth, weakly curved manifold, in a fixed topology, and certainly we live in 4 space-time dimensions. All of these features in string theory are somewhat nebulous. String theory, the singularities that one encounters in classical field theory, quantum field, perturbative quantum field theory, are always cured. And thus one can change the topology of space-time in string theory without any problem. In fact, one, in some cases, must consider superpositions of topology. And even the number of space-time dimensions becomes a somewhat nebulous question. So we have for many years believed that space-time has got to be an approximation to something else, or an emergent concept, good at large distances, but requires a different framework to explain at short distances or high curvature. I myself have no doubt that space-time is emergent, will be understood that way. It's beginning to be understood that way. Gravity as well, of course, as gravity is the dynamical theory of space and time. But how exactly precisely in all circumstances is perhaps the most difficult question on my bucket list, and but the one which I'm most confused about. Most of the insights have come from duality, ADS-CFT duality, between a duality, if you want, between in string theory between open strings description and closed string descriptions, or between, but specifically, the examples that made this most precise and have been most informative for the last 25 years has been the duality of strings in ADS space and an ordinary quantum mechanical non-gravitational theory in the boundary of ADS space, which is kind of a box with a boundary which is can be described by ordinary four-dimensional Minkowski space. So quantum mechanics is quantum field theory is a theory we think we know what the principles are. We have examples of successful quantum field theories like QCD. We think we know what we're doing. And the remarkable duality of that description of a theory to theory of strings, or at long distances of dynamical space-time of gravity in anti-de Sitter space, gives us a way of understanding what string theory is, what the rules are, a formulation of non-perturbative formulation of string theory in this particular case. And this duality is informative in both directions. Gives us, in some cases, information about gauge theories or conformal field theories in general in using information from semi-classical gravity, which we do think we understand, and vice versa about string theory based on our control and understanding of quantum field theory. Quantum field theory and string theory are not different theories, and not different. They're part of a general framework and different often, as in this duality, different ways of looking at the same physics. There are many aspects of this that we've learned from this duality, but it has, for example, in my opinion, resolved one of the potential paradoxes of quantizing gravity and the black holes paradoxes, which Hawking raised years ago, claiming that black hole formation and evaporation would violate quantum mechanics. Black holes, being black, can't communicate with the outside. Hawking radiation means they evaporate. Information is lost. That violates quantum mechanics. Hawking even went so far as to say, if that's the case, you would have virtual black holes. And that would violate quantum mechanics, even in situations where macroscopically or there are no real black holes. It's a real challenge to quantum mechanics, which has been answered by this duality, because one can map quantum gravity in space-time to quantum mechanical systems on the boundary of that space, if you have a boundary. There's kind of a duality between a black hole, in the case of ADS-5, the gauge theories which on the quantum mechanical dual side are supersymmetric gauge theories, cousins of QCD, and share many of its properties. In particular, they have kind of unstable fireballs, which are like black holes. You shoot in a lot of quarks, gluons, they form a fireball, which then radiates away. And of course, that's a purely quantum mechanical time evolution, which preserves information, is unitary. And that clearly demonstrated that to most of us that information is conserved, there's no contradiction. And in the last 20 years, there's been enormous progress, especially recently. I think we're going to hear about that from Juan in the next lecture. But much more than that, not just resolving the paradoxes of black holes, but also in general, we're beginning to explain how the geometry of space and time in our theory of gravity emerges from the nature, from the quantum states, in the case of ADS, on the boundary of that space-time. So this duality has now provided us with the beginnings, and just the beginnings of an understanding of what it might mean for space-time to be emergent. And the most remarkable thing is the connection between the emergence of geometry of space-time and the dynamics of space-time in terms of the specific nature of the quantum states on the boundary, and in particular on the entropy, on the entanglement of these states. There's a beautiful and rapidly developing field. It has so far been enormously illustrative for the case of ADS, which has a nice boundary. It's not at all clear yet how to do this, explain how this emerges in other space-times, like flat space or de Sitter space that we appear to be living in on a cosmological scale. And this brings me to try to connect the themes of this talk. In a unified theory, which includes gravity, the dynamics of space-time, the answer, what we're trying to describe, is the universe. And can't avoid that. And the universe, of course, is this space-time history. And it has a beginning, and it has a boundary, maybe, or no boundary, and it has an end. So if you have an answer to the theory of everything, you have a potential candidate for a history of space-time, the universe. You have an answer which contains the beginning, the end. Those are crude terms because we really understand nothing about what happens or could happen at the beginning or the end. We don't really know what the rules are. Again, we're trying to describe a particular, a solution. But what are the rules that pick out that solution? How did the universe begin or end? We always focus on the beginning, but the laws of physics are time reversal invariant. And the end is, in my opinion, an equally valid and interesting question. So normally this is, what is the initial condition? How did the universe begin? What state did it begin? Is it the Hartle-Hawking state, which is kind of a complex detour into the complex space-time, so there's no beginning really, no meaning to beginning or end? Or is it a particular state? And it's even more complicated in quantum mechanics, where there might be multiple states with different and who determine. Can we determine the initial condition? Can we determine the final condition? Maybe we need to determine the final condition to pick out a unique solution. Is there a unique solution, or just a multiverse of probable universes? The reason this sounds much too complicated to be put on my bucket list, maybe on one of your bucket lists for the young people, but I think it's kind of necessary, because in particle physics, we have signs that all the forces and gravity should unify. We have frameworks in which they could. Superstring theory provides that. The only problem is there's so many possibilities and we don't know what the principle is. Maybe what picks out the particular theory, particular compactification of string theory, particular theory from this very powerful and apparently consistent framework, is the beginning and the end, the answer to the question of how we pick, what picks out the particular initial condition. Any potential compactification, KTLT of string theory, whatever, has a beginning which we don't understand. And it could be that all of those landscape of possibilities are inconsistent with our understanding of the beginning or the end, or both, of time. So I personally think that these might be connected, that we couldn't understand the unification without understanding the initial condition, and these are connected. And obviously, they're then connected with the third item in my bucket list, the nature of space and time. These are the most difficult questions to try to understand what emergent space-time is, how space-time emerges to give us not just EDS, but flat space, de Sitter space, etc. So these are all difficult questions. I'm always encouraged by Einstein's encouragement. He wrote once, "The successful attempt to derive delicate laws of nature along a purely mental path," which is what us theorists try to do, "by following a belief in the formal unity of the structure of reality, encourages continuation in this speculative direction. But the dangers of which everyone vividly must keep in sight who dares follow it." But for the young people in this audience, there aren't many, but there are a few, I offer the optimistic belief, based on my reading of history and personal experience, that once a fundamental question becomes a well-formulated and scientific question, which means that it's approachable by science, by experiment, by observation, and mathematical modeling, it will be answered in your lifetime. That's reassuring. These are wonderful questions. But the issue, of course, is your lifetime. So these are the three items of my bucket list, which I hope will be answered in my lifetime. But I'm not sure of that. I certainly will need a long lifetime. And here I can come back to Mani, who's a great example of 91, my God. Look at him. How does he do it? I've learned at least 3 secrets that Mani has taught me about. how to live a vibrant, long lifetime. Good food, good wine, good physics. So happy birthday, Mani.
Mike, we have some questions from the audience. Everything's perfectly clear. That was a great talk.
Well, give him time.
Well, then let's thank David again. And then. Thanks. There's coffee and we'll meet at 11:20. And there's doors that can go outside. So if you want to be outside.